Hello everyone. Today I'm going to introduce our work, Randomized Quantization. It is a generic augmentation designed for self-supervised learning that can be applied to any data modality. Existing Siamese representation learning relies on data augmentation as a supervisory signal. However, the problem is these augmentations are modality-specific, and the effectiveness of augmentations in one domain can hardly be transferred to the other. Representative data agnostic self-supervised learning are extended from mix-up. Given their generality, their performance is limited, which we will show in our experiments. The key insight in our augmentation is to conduct masking in channel dimension. We draw inspiration from the effectiveness of sequential masking for self-supervised learning. Specifically, mixed image modeling or simply masking input as an augmentation has emerged as an effective approach for self-supervised learning. However, the masking scheme is usually conducted on sequential dimension. For example, sequential dimension can be spatial in images, temporal in audios, and synthetic in languages. Orthogonally, in this work, we explore masking in channel dimension, which is domain generic. The technique we proposed for that is randomized quantization. Quantization represents numerical values with a fixed discrete set of numbers. In operation, a quantizer maps values within an interval to a single scalar. But a quantizer in its most commonly used sense is not immediately suitable to serve as effective data augmentation. Firstly, the process of quantization is deterministic. Secondly, the produced numbers are designed to share similar behaviors as the input. Therefore, the complexity and strength of such augmentation is limited. In this regard, we design a complex quantization augmentation by randomizing the intervals and the reproduction values. Specifically, the intervals are randomly sampled, and for input values inside each quantization bin, the output values are randomly sampled from this bin. Aside from randomizing intervals and reproduction values, we can control the complexity of this augmentation by adjusting the number of bins. We visualize the augmentation for images, point clouds, and audios. On images, it removes the high-frequency details but highlights object boundaries and edges. It also alters color appearance significantly. On point clouds, where channel dimension represents 3D coordinates, it tends to downsample local structures but highlights the global shape. On audios, we find the augmentation tends to enhance specific frequency signal, such as low frequency or high frequency sounds. We ablate 3 design factors of the proposed augmentation, which affect its ability to mask channel-wise information. We choose visual representation learning for the ablation study. The experiments are conducted under MoCo V3 framework. The baseline is random resized cropping, in other words RRC, and then we apply our augmentation on top of it. We can easily observe performance gain by randomizing bins and randomizing the reproduction values. We vary the number of bins and find a strong performance with 5 to 10 bins, peaking at 8. We examine pre-training with the proposed augmentation across a variety of modalities. On image domain, our method surpasses alternative domain agnostic self-supervised learning by large margins. On point clouds, our method also outperforms the state-of-the-art self-supervised methods for both shape classification and segmentation. For audio representation learning, randomized quantization can also surpass the existing state-of-the-art. On all modalities of the public benchmark DABS, randomized quantization outperforms the baseline. In summary, the effectiveness of randomized quantization has been validated across various data modalities under different self-supervised pre-training schemes and under various backbone networks. The code has been released and you are welcome to try it in your work. Please feel free to contact us if you have any questions. Thank you a lot for your attention.